hemostatic agent that you use in this brain surgery will be very valuable for us if we can use it, and it's regarding the experience. I mean, your experience, maybe we can have some view of that. Okay, we will have the last speaker. The last speaker come from China as well, from Medfrin Biotech GmbH, Ms. Xinzhi Zhang, PhD. She is an academic director in this company, and we hope that we can see what the product that Ms. Xinzhi Zhang can propose to us as a good product, or we can also see if it is usable or not. So I think Dr. Xinzhi Zhang can present the topic about the specific product for the hemostatic. Dr. Ms. Xinzhi Zhang, time is yours.
Great, thank you. Hi, everyone. So before I get started, I really would like to thank the company for providing us this opportunity to, showcase StypCel. So let me start to share my screen.
Okay, the committee can support. Okay.
Okay.
Yeah.
So today, so you can see the screen.
Yeah. Yes.
Yes. Clear. So today I want to share with you StypCel, the absorbable hemostat from Medfrin. So we all know it's very important to achieve intraoperative hemostasis. Dr. Al-Fawzi at the earlier session also mentioned the importance. So a successful intraoperative hemostasis could provide clear view of the surgical site. It will lead to successful wound management. It could prevent adverse physiological effects associated with blood loss. And also this could reduce in surgical time as well as the need for blood transfusion. There are typically three types of bleeding: artery bleeding, venous bleeding, and also capillary bleeding, which are associated with their own characteristics. So in the surgery, meaning three types of methods are being used for achieve surgical hemostasis. We have mechanical ways, using clamps or ligation. We'll have thermal or energy-based ways to achieve hemostasis, such as the bipolar forceps. And we can also use chemical ways using the drugs and pharmaceutical agents to help to achieve hemostasis. So here we have a very short presentation of blood clotting mechanism, as Dr. Alfreda also have mentioned. So the first step is really after the injury of the vessel is going to constrict, trying to limit the volume of the blood that can be escaped from the damaged site. And then those platelets, they are going to accumulate at where the vessel is injured to form what we call a platelet plug. And then this platelet plug is going to be activated by the cascade, the hemostasis cascade. And then the fibrin is actually, the fibrinogen from the platelet is going to be released and then convert into fibrin to form a fibrin mesh, which leads to the first kind of formation of clot. And this will eventually lead to blood coagulation. So StypCel actually helps in the platelet plug formation step, which I will elaborate later in this presentation. So StypCel is made from oxidized regenerated cellulose, or ORC. It is sterile, looks like a piece of gauze and is thrombogenic. And cellulose comes from plant and then kneaded and oxidized to form this ORC. So the material itself can be absorbed without causing foreign body reaction in the long term, and it acts as a scaffold for clot formation. So ORC has been widely used in disposable medical devices, and also because of its low pH, it actually has antibacterial properties, which helps to minimize the risk of infection after the surgery. So you might heard hemostat made from OC or oxidized cellulose. So here I want to just kind of distinguish OC and ORC. So the oxidized cellulose is made from cotton cellulose. Basically, the cellulose from the cotton is being extracted. Those fibers are then directly oxidized to form oxidized cellulose. However, for the ORC, first of all, the source of cellulose is a little bit different. So wound pulp cellulose is being first physically extracted and then dissolved chemically to form a solution. This solution is then regenerated to form fibers by a spinning process. So those regenerated fibers are then oxidized to form the oxidized regenerated cellulose. So because of the method that how OC and ORC are being made, their structure actually are different from each other. So on the left, you can see the OC fibers, which are oxidized irregular structure. On the right, you can see the ORC fibers, which are homogeneously regenerated. So because of this, products made from OC have certain limitations. The first is because of the lack of those special regeneration process. The composition of those fibers actually is affected by the growing conditions, as batch of cotton grow in different years or at different geological areas, vary in chemical and physical properties. And those fibers from OC, they remain their nature properties, which result in an uneven diameters throughout their length. As you can see on the picture, those fibers on the left, they actually have different diameters. And because of this, there's a lack of uniformity in terms of degradation, which could further prevent epithelialization and decrease the wound healing speed. So how StypCel actually works in terms of helping to achieve hemostasis, we can actually consider it helps in two different aspects. So the first aspect is really a physical method. So when in contact with blood, StypCel will dissolve and swell and dissolve into a gelatinous material, which acts as a physical barrier. This physical barrier helps to block blood flow. But another aspect is really a biological reaction. So the red blood cells and platelet, they form the aggregate. When StypCel is applied, because of the low pH, the red blood cell is going to be disrupted in this environment. And the myoglobin in the red blood cell is going to be liberated, which will accelerate the coagulation cascade, and which helps to transform fibrinogen into the fibrin clot. And this clot will eventually help to stop bleeding. So that's how StypCel actually works. So the indication of StypCel is when there's capillary, venous, or small artery bleeding, and when ligation or other conventional methods are impracticable or ineffective in neurosurgery. So here is a demo of how it's being used in neurosurgery, and later I have some clinical cases to share. So we looked into the safety of StypCel, and by implanting a small piece of StypCel in the muscle of a rabbit, and then we looked into how long will it take for for it to degrade. And we find that after 2 weeks, StypCel actually was completely absorbed, meaning it will not lead to foreign body reaction in the long term. So we believe StypCel is a very good candidate for hemostasis in neurosurgery because it has outstanding benefits. So the first is efficacy. Here we have an example comparing StypCel to a control group, which is SurgiCel Fabryla that is being used quite often in neurosurgery. So if you look at the top of this scanning electron microscope, you will find the microstructure of StypCel, and the bottom is the control group. So not only StypCel has longer and slender fibers, but also those fibers are more packed more densely, which means when the same size of hemostat is in contact with the bleeding area, there's actually larger specific contact area between the fibers and blood, which improves the efficacy, as you can see from the video here. So on the left is StypCel, on the right is the control group. So StypCel actually prevents further spreading of the blood. We then also quantified this efficacy and looked into the hemostatic rate with a rabbit model. So in this model, a 1 by 1 by 0.2 centimeter incision was made on the liver of the rabbit. Then we apply either a piece of StypCel or the same sized control group, again, SurgiCel Fabryla, onto the incision. And then we looked into the time for it to take the liver to achieve a complete hemostasis. So here you can find the distribution of time to achieve hemostasis. And for StypCel, half of it achieved hemostasis within 60 seconds. And that number for the control is that actually it takes much longer. 9 out of 23 samples for the control group achieved hemostasis after 200 seconds. And we looked into compared the significant, the difference between the average time to achieve hemostasis, and we find that StypCel actually have a significantly faster hemostatic rate. We also looked into percent of samples to achieve hemostasis within 2 minutes, and we find this number was 73 for StypCel and only 20% for the control group. We also looked into the amount of bleeding before hemostasis was achieved. And we find that for the StypCel treated group, less than 1 gram, 93% of the rabbits achieved hemostasis with less than 1 gram of blood loss, while this number was only 20% for the control group. So here we have the kind of the image taken during the surgery. And we can find that on the left is StypCel, in the middle is SurgiCel Fabryla, and then on the right is SurgiCel Original. So for StypCel, hemostasis was already achieved, while for SurgiCel Fabryla and SurgiCel Original treated groups, they are still bleeding at the same time. SurgiCel is also easy to handle. We apply them in different layers. Those layers are easy to peel, and they can be easily shaped to be applied to irregular structures, which means you can use them in the endoscopic procedure. SurgiCel also have very excellent conformity to the surgical site, which enhances the contact between StypCel and the blood, which enhances hemostasis. Here we have optional sizes for StypCel. So we apply them in 6 layers, 8 layers, or 10 layers. And we have the smallest from 2.5 to 2.5 to the largest, which is 10 by 10 centimeter, to accommodate your needs during the surgery. So just a quick comparison between StypCel and SurgiCel Fibrilla. They were made from the same material. They are all non-woven, and absorption time is the same. However, StypCel comes in 6, 8, and 10 layers, while SurgiCel Fibrilla has only 8-layer design. In general, StypCel achieves hemostasis faster than the Fibrilla because of the longer, slender, and more densely packed fibers of StypCel. So here I want to show you some clinical application of StypCel. So this one is a transsphenoidal application in the pituitary tumor removal. And this comes from a neurosurgery in Jordan. So he actually applied StypCel layer by layer to ensure hemostasis is achieved. Here we have another example of StypCel in the skull-base region. It's a Chiari malformation. So the surgeon takes a piece of StypCel and kind of roll it into a cylinder and place it into the region that needs to achieve hemostasis. As you can see, it did not stick to the bipolar forceps. Here's another example, is in cervical spinal canoe, and this is after removal of the space-occupying lesion. So the surgeon took a piece of StypCel and peeled it into different smaller layers, and he's actually applying StypCel layer by layer onto the lesion where he wants to achieve hemostasis. So it's the same piece of StypCel, different layers. I believe the size for this StypCel is 2.5 by 2.5. And then after applying StypCel, he also used cautery to cut through the StypCel to ensure complete hemostasis. So that concludes our presentation on the product StypCel, and thank you for your time.